There are places in our solar system that seem almost deliberately designed to break our idea of what a world should look like. On one of them, rain falls from an orange sky. Rivers carve valleys into the landscape, and enormous seas stretch toward the horizon. Yet not a single drop of that liquid is water. On another, the ground is constantly being torn apart from within as the gravity of a nearby giant planet repeatedly squeezes the entire world and feeds volcanic eruptions on a scale unlike anything we see on Earth. These places are not distant exoplanets orbiting some alien star. They are Titan and Io, two moons hidden within our own solar system, and the closer we look at them, the stranger they become. You're watching Beyond Horizon, where we explore the strangest places our universe has to offer. Our journey begins roughly 1.4 billion kilometers from the Sun in orbit around Saturn, where more than 100 known moons accompany the planet on its path through the solar system. Most are small, irregular bodies, but one of them is so large that if it orbited the Sun instead of Saturn, we would almost certainly think of it as a world in its own right. Titan is the largest moon of Saturn and the second largest moon in the solar system. With a diameter of about 5,150 kilometers, it is larger than the planet Mercury, although its much lower density means it contains considerably less mass. Yet size is not what makes Titan extraordinary. What really separates it from almost every other moon we know is something surrounding it. An atmosphere so substantial that standing on Titan's surface would place you beneath an atmospheric pressure roughly 1.5 times that experienced at sea level on Earth. For a moon, this is remarkable. Our own moon has almost no atmosphere at all, while even Mars possesses only a thin remnant of what it once had. Titan, by contrast, is wrapped in a dense atmosphere dominated by nitrogen, the same element that makes up most of the air on Earth. Mixed into it is methane, along with a complicated collection of hydrocarbons and organic molecules produced by reactions occurring high above the surface. From space, this atmosphere makes Titan look almost featureless. Instead of mountains, craters, or valleys, an approaching spacecraft sees a smooth orange sphere covered by a thick photochemical haze. For decades, that haze prevented astronomers from knowing what was actually hiding underneath. When Voyager 1 passed through the Saturn system in November 1980, Titan was one of the mission's most important targets. Scientists already knew that it possessed an atmosphere, and Voyager confirmed that this atmosphere was remarkably dense, but its cameras could not penetrate the orange haze. The surface remained hidden, and in some ways the encounter created an even greater mystery than the one it had been intended to solve. It would take another spacecraft and more than 2 decades before humanity finally saw what was underneath. In 2004, the Cassini spacecraft entered orbit around Saturn, carrying an instrument that did not need visible light to see Titan's surface. Its radar could send radio waves through the atmosphere and measure the signals reflected back from the ground. Gradually, flyby after flyby, a completely unexpected landscape began appearing on scientists' screens. There were mountains, enormous fields of dunes and channels that looked disturbingly familiar. Some branched into smaller tributaries, while others crossed the landscape toward broad, dark regions whose surfaces were so smooth that they reflected almost no radar energy back toward Cassini. Eventually, there was little doubt about what these dark regions represented. They were lakes. This alone would make Titan one of the most remarkable places ever discovered, because Earth and Titan are the only worlds currently known to possess stable bodies of liquid on their surfaces. But at Titan's average surface temperature of around -179 degrees Celsius, those lakes cannot possibly be filled with liquid water. Water on Titan behaves more like rock does on Earth, frozen so solidly that it forms much of the moon's crust. Instead, Titan's lakes and seas are filled primarily with liquid methane and ethane. The largest of them, Kraken Mare, is enormous. It stretches for roughly 1,200 kilometers across Titan's northern polar region, while nearby Ligea Mare spans about 500 kilometers. Surrounding these great seas are hundreds of smaller lakes, creating a landscape that, when reconstructed from Cassini's radar observations, can look surprisingly similar to a terrestrial coastline. And this is where Titan becomes much stranger than simply being a frozen moon with hydrocarbon lakes, because those liquids do not just sit motionless on the surface. They participate in something that looks remarkably similar to the hydrological cycle on Earth. On our planet, sunlight heats the oceans, causing water to evaporate into the atmosphere. That water forms clouds, eventually returns as rain or snow, flows through streams and rivers, and finally collects again in lakes and oceans. Titan operates according to essentially the same broad principle, except that its weather system substitutes methane for water. Methane evaporates from lakes and seas, enters the atmosphere, condenses into clouds, and can eventually fall back toward the surface as rain. That rainfall can flow downhill, carving channels through the landscape before eventually returning to lakes and seas. Recent observations with the James Webb Space Telescope have even detected methane clouds over Titan's northern hemisphere, adding another piece to a weather system that Cassini spent years trying to understand. If you could somehow stand on Titan while protected from the extreme cold, the landscape might therefore feel strangely recognizable. You could watch clouds move across the sky, see hills and valleys in the distance, and perhaps stand beside the shore of an enormous sea while waves moved across its surface. Somewhere beyond the horizon, rainfall could be feeding rivers that eventually emptied into the same sea. But almost every familiar detail would be made from the wrong material. The rocks beneath your feet would contain enormous amounts of water ice. The rivers would carry methane. The seas would contain methane and ethane, while the orange sky above you would be filled with organic haze created by chemistry occurring hundreds of kilometers overhead. Even the dunes would be alien. Cassini discovered vast dune fields around Titan's equatorial regions, some extending for hundreds of kilometers. Instead of being composed primarily of silicate sand, like many deserts on Earth, Titan's dunes appear to contain complex organic material that has fallen out of the atmosphere and accumulated on the surface over enormous spans of time. That material begins its journey high above the ground, where sunlight and energetic particles interact with methane in Titan's atmosphere. Methane molecules can be broken apart, and their fragments participate in increasingly complicated chemical reactions, eventually producing larger carbon-rich molecules. Some of these products descend through the atmosphere, helping create Titan's characteristic orange haze before eventually reaching the surface. This makes Titan interesting for a reason that goes far beyond unusual weather. The chemistry taking place there may resemble, in certain respects, processes that occurred on the young Earth before life transformed our planet. Titan is certainly not a replica of early Earth. Its temperatures, chemistry, and environment are radically different. But it provides scientists with something extremely rare: a natural laboratory where complex organic chemistry is taking place on a planetary scale. And then, in January 2005, humanity actually landed there. Attached to Cassini was a small European probe named Huygens. After separating from the spacecraft, Huygens entered Titan's atmosphere and began a descent lasting more than 2 hours. As it fell through the haze, its cameras gradually revealed the landscape below, providing the first direct images ever taken beneath Titan's clouds. What appeared looked almost unsettlingly terrestrial. The images showed bright highlands crossed by dark branching channels leading toward lower terrain. Rounded pieces of water ice were scattered around the eventual landing site, their shapes suggesting that flowing liquid may have transported and eroded them in the past. Huygens survived its landing and transmitted data from the surface, giving humanity its first view from the ground of a world in the outer solar system. Yet perhaps the most important thing about Titan is that everything we have described so far may represent only its outermost layer. Gravity measurements and models of Titan's interior suggest that deep beneath its frozen crust, there may be an enormous reservoir of liquid water, potentially mixed with substances such as ammonia that could help keep it from freezing. If such an ocean exists, Titan would contain two completely different liquid environments separated vertically from one another. Hydrocarbon seas exposed to the atmosphere above, and a buried water ocean hidden beneath kilometers of ice. That combination makes Titan unlike almost anything else we know. On its surface, chemistry operates without liquid water, using methane and ethane under conditions far colder than any natural environment on Earth. Far below, however, a water-rich ocean may have existed for billions of years. Scientists do not currently know whether either environment could support life, and there is no evidence that life has been discovered on Titan. But both environments force us to confront a much larger question. How different could the chemistry of a living system be from the chemistry of life on Earth? NASA is preparing to investigate some of those questions with Dragonfly, a rotorcraft designed to travel between multiple locations on Titan and examine its surface chemistry. Rather than remaining at a single landing site, Dragonfly is intended to fly through Titan's dense atmosphere, moving across a landscape that Cassini and Huygens could only begin to explore. But before we leave Titan, there is one final mystery worth considering. Methane should not simply remain in Titan's atmosphere forever. Sunlight continually destroys it in the upper atmosphere, breaking methane apart and allowing its components to form other hydrocarbons, while some hydrogen ultimately escapes into space. Without some process replenishing the methane, Titan's present atmosphere cannot remain exactly as it is indefinitely. That means the world we see today may represent only one chapter of Titan's history. Its orange atmosphere, clouds, rainfall, rivers, and enormous hydrocarbon seas could be part of a planetary system that is slowly changing over geological time, just as Earth's environment has changed repeatedly throughout its own history. And that is what makes Titan so extraordinary. From a distance, it appears to be little more than an orange moon orbiting a giant planet. Once we penetrate the haze, however, we find weather, coastlines, rivers, dunes, complex organic chemistry, and perhaps an enormous ocean hidden deep underground. It is a world where many of the processes we associate with Earth have somehow reappeared using completely different ingredients. Yet Titan is only the first half of our journey because much closer to the Sun, orbiting another giant planet, nature has created almost the exact opposite. Instead of a world shaped by extreme cold, the next moon is being heated relentlessly from within. Instead of hydrocarbon rain slowly carving valleys over immense periods of time, molten rock continuously destroys and rebuilds the landscape. And unlike Titan, whose surface can appear eerily calm, this world is trapped in a gravitational mechanism from which it cannot escape. To understand it, we have to travel from Saturn to Jupiter, where a moon roughly the size of our own is being physically distorted every time it completes an orbit. And somehow it has survived this punishment for billions of years. Io, the world Jupiter refuses to let rest. Io orbits Jupiter at an average distance of only about 422,000 kilometers, which is remarkably similar to the distance separating Earth from our own moon. At first glance, the comparison seems almost reasonable. Io is only slightly larger than the moon, both are rocky bodies, and both are locked in synchronous rotation, permanently showing roughly the same hemisphere toward the planet they orbit. If distance and size were all that mattered, we might expect Io to resemble the familiar gray, cratered world hanging in Earth's night sky. Instead, Io looks like something produced by an entirely different set of physical rules. Its surface is covered in yellow, orange, red, white, and black deposits, creating a landscape so unusual that early images of the moon were unlike anything planetary scientists had seen before. Large impact craters, one of the defining features of almost every old rocky surface in the solar system, are essentially absent. The reason is not that asteroids somehow avoid Io, but that the surface is being renewed so rapidly that the scars they leave behind are repeatedly buried beneath new volcanic material. We did not know any of this until 1979. That year, NASA's Voyager 1 spacecraft passed through the Jupiter system and returned the first detailed images of Io. Shortly after the encounter, navigation engineer Linda Morabito was examining one of the images when she noticed something extending beyond the edge of the moon. At first, it appeared almost like another object behind Io, but further analysis revealed something far more important. Voyager had photographed an enormous volcanic plume rising above the surface. For the first time in history, humanity had observed an active volcano on another world. What made the discovery even more remarkable was that scientists had actually predicted something like it shortly before Voyager arrived. Researchers Stan Peele, Patrick Casson, and Ray Reynolds had calculated that the gravitational interaction between Io, Jupiter, and the neighboring moons Europa and Ganymede should generate an extraordinary amount of heat inside Io. Voyager then arrived and provided dramatic evidence that this theoretical prediction described a real world. The mechanism responsible begins with Jupiter itself. With more than twice the mass of all the other planets in the solar system combined, Jupiter dominates the gravitational environment around it. Io travels deep inside that environment, completing an orbit in only about 1.77 Earth days. If Io followed a perfectly circular orbit, the gravitational distortion caused by Jupiter would remain relatively constant, and much of the extreme heating would eventually diminish. But Io is not allowed to settle into such an orbit. Europa and Ganymede continually interfere with it through an orbital relationship known as the Laplace resonance. For every orbit completed by Ganymede, Europa completes approximately 2, and Io completes approximately 4. Because these gravitational encounters occur in a regular rhythm, they continually maintain a slight eccentricity in Io's orbit rather than allowing Jupiter's tides to circularize it completely. That tiny deviation from a perfect circle has enormous consequences. As Io moves closer to Jupiter, the difference in gravitational force across the moon becomes stronger. The side facing Jupiter is pulled slightly more strongly than the far side, stretching the entire body. As Io moves farther away again, that distortion relaxes. The process repeats continuously during every orbit, flexing solid rock on a scale that is difficult to imagine from our experience on Earth. NASA estimates that these solid body tides can raise and lower Io's surface by as much as about 100 meters. On Earth, the most familiar tides move water through our oceans. On Io, Jupiter's gravity moves the moon itself. All of that repeated deformation produces friction and dissipates energy inside Io as heat. Over billions of years, the effect has been sufficient to make Io the most volcanically active world known in the solar system. Instead of preserving an ancient surface like Earth's moon, Io continuously brings material from its interior upward, covering older terrain with new lava flows and volcanic deposits. Hundreds of volcanoes have been identified across the moon, and some eruptions produce plumes that rise hundreds of kilometers above the surface. Lava fountains can extend for tens of kilometers, while enormous volcanic depressions, known as padorae, scar the landscape. Sulfur and sulfur dioxide released by this activity contribute to the extraordinary colors seen across Io, producing a surface that can change noticeably between spacecraft encounters. This is why Io contains so few obvious impact craters. The surface simply does not remain undisturbed long enough to accumulate the ancient record seen on bodies such as Callisto or Earth's moon. every new eruption contributes to an ongoing geological reset, making parts of Io's landscape some of the youngest terrain anywhere in the solar system. Among all these volcanic systems, one stands apart. Loki Patera is an enormous volcanic depression, roughly 200 kilometers across, and one of the most powerful, persistent sources of heat on Io. Observations spanning decades have shown repeated changes in its thermal output, and spacecraft have revealed a vast, dark volcanic region whose behavior has fascinated planetary scientists since the Voyager era. The scale becomes easier to appreciate when compared with Earth. A volcanic feature 200 kilometers across would dominate an enormous portion of any terrestrial landscape. On Io, it is simply one component of a global volcanic system containing hundreds of active centers. And even after Voyager discovered this world, we were only beginning to understand it. NASA's Galileo spacecraft arrived at Jupiter in the 1990s and repeatedly observed Io, obtaining much sharper views of its volcanoes, lava flows, and changing surface. New Horizons later photographed volcanic activity while using Jupiter for a gravitational assist on its way to Pluto. More recently, Juno has returned to Io with instruments capable of examining the moon in visible light, infrared, and even microwave wavelengths. During close approaches in December 2023 and February 2024, Juno passed within roughly 1,500 kilometers of Io's surface, providing the closest spacecraft observations of the moon in more than 2 decades. The encounters revealed extraordinary details in volcanic terrain and allowed scientists to investigate how heat is distributed across the surface and beneath it. Those observations are particularly important because a major question about Io remains unresolved. Exactly where inside the moon is all of this heat being generated, and how is molten material distributed beneath the crust? For years, one possibility was that Io might contain a nearly global ocean of magma beneath its surface. Such an ocean would provide an intuitive explanation for a world covered in hundreds of volcanoes. However, measurements of Io's response to Jupiter's gravity have complicated that picture, and scientists continue to investigate whether the interior is dominated by a global molten layer or by a more complex mixture of solid and partially molten regions. The newest observations are beginning to probe that hidden world more directly. Juno's microwave radiometer has measured heat coming from several meters beneath the surface, allowing scientists to look below the thin layer that infrared instruments normally observe. The results reveal significant shallow subsurface heating and reinforce the idea that Io's enormous internal energy is distributed through a complicated geological system rather than behaving like a simple uniform furnace. Yet volcanism is only part of what makes Io such an extreme place. The moon also travels through Jupiter's enormous magnetosphere, where electrically charged particles interact with material escaping from Io's atmosphere and volcanic plumes. Sulfur and oxygen originating from Io become ionized and form a vast ring of plasma around Jupiter known as the Io plasma torus. The motion of Io through Jupiter's magnetic field also generates enormous electrical currents connecting the moon and the planet. In a very real sense, Io is not merely orbiting Jupiter. It is electrically and gravitationally connected to it. This relationship makes the moon a striking example of how misleading the word world can be when we imagine planets and moons as isolated objects. Io cannot be understood on its own because almost everything extraordinary about it is being driven by the larger systems surrounding it. Jupiter supplies the immense tidal force, while Europa and Ganymede help preserve the orbital conditions that prevent Io from escaping its cycle of deformation and heating. Remove that gravitational architecture, and the Io we know today would eventually cease to exist. And that brings us back to Titan. At first, these two moons could hardly appear more different. Titan lies far from the sun beneath a thick nitrogen atmosphere where temperatures are cold enough for methane to behave much like water does on Earth. Io possesses almost no substantial atmosphere and is dominated instead by relentless volcanism generated deep within its interior. Titan's landscapes are shaped by rainfall, rivers, dunes, and hydrocarbon seas, while Io's surface is repeatedly destroyed and rebuilt by lava. Yet the same broader lesson connects them. Neither world became extraordinary in isolation. Titan's distance from the sun allows methane and ethane to remain liquid on its surface, while its atmosphere supports an active weather cycle. Io's position beside Jupiter and its resonant relationship with neighboring moons turn orbital motion into internal heat. In both cases, the environment surrounding a world determines what that world can become. For much of human history, our understanding of the solar system was built around a small collection of familiar objects. There was the sun, the planets, our moon, and a scattering of distant points whose true nature remained unknown. Even after telescopes revealed additional moons, they were often treated as secondary objects, interesting mainly because they happened to orbit planets. Spacecraft changed that perspective completely. When Voyager reached Io, it found active volcanoes where scientists might once have expected an old, cratered surface. When Cassini arrived at Titan, it discovered a world with weather, rivers, and seas hidden beneath an atmosphere that had concealed the surface from telescopes. Each discovery forced us to expand our definition of what a planetary environment could actually be. And perhaps that is the most important reason to study worlds like these. When astronomers search for potentially interesting planets around other stars, it is tempting to imagine that the most important discoveries will be worlds resembling Earth. A rocky planet at the right distance from its star, with liquid water and a familiar atmosphere, naturally attracts our attention because it resembles the only inhabited planet we know. But our own solar system demonstrates how limited that intuition may be. Nature has created stable seas from methane, maintained volcanic activity through orbital resonance, hidden enormous oceans beneath frozen crusts, and produced complex organic chemistry in environments where surface liquid water cannot exist. None of these worlds is a second Earth, and that is precisely what makes them valuable. Titan and Io show us that the laws of physics do not produce one standard kind of planet or moon. Give the same basic ingredients, different temperatures, different atmospheres, different gravitational relationships, and enough time, and the results can become almost unrecognizable. We have explored only a tiny fraction of these environments directly. Huygens operated on Titan's surface for only a short time. No spacecraft has ever landed on Io. Much of what lies beneath both moons remains inaccessible, reconstructed indirectly through gravity, magnetic fields, chemistry, and radiation. And these are worlds orbiting planets in our own cosmic backyard. Beyond the solar system, thousands of planets have already been confirmed around other stars, occupying environments far more diverse than anything early astronomers imagined. If Titan and Io can exist around two neighboring planets orbiting the same sun, then the range of worlds waiting elsewhere in the galaxy may be far stranger than anything we have discovered so far. The strangest worlds in the universe may therefore not be the ones that violate the laws of nature. They may simply be the ones that reveal how much those laws are capable of creating. And perhaps one day, when our telescopes become powerful enough to see them clearly, we will discover that the strangest worlds we know today were never really that strange at all. They were simply the first ones we were able to reach. If you enjoyed this journey, subscribe to Beyond Horizon. There are still countless worlds left to explore, and this is only the beginning.